Hey everybody. Today we are talking about section 1.4 in the textbook called Logarithmic Functions. Now in section 1.2 we talked about a type of function called an exponential function, and in section 1.3 we talked about inverse functions among other things. An inverse function is kind of the opposite of the original function. So we had this picture with functions where we had some box and we passed in an input and we got the output. The inverse function is the one that works like if you turned the box in reverse. You put in a certain output and you get what the input was for it. So logarithmic functions are the inverses of those exponential functions. So that's why they're important. Exponential functions have a base, right? Their general form was a to the x, and sometimes there was a constant and some other stuff, but they have a base a and they're raised to some power x. And since they have a base a, their inverse functions also have a base a. There, we write them kind of like this. So we have log for logarithmic. We have a in kind of a subscript there. And then we have our input x. So the way that you read this out loud when you see it is that this is log base a of x. So on the left here, we have some graphs. We have the graph of 2 to the x. We saw in section 1.2 what those general exponential functions look like. They go down very, very close to 0 on the left-hand side. They cross at 0, 1, that's their y-intercept, and then they go off up to infinity pretty quickly on the right-hand side. Well, since the log base 2 of x is the inverse of 2 to the x, we kind of know what it has to look like. In section 1.3, we said the inverse function is kind of the symmetry of the original function over that diagonal line y equals x. So if you take this function and you flip it over the line, you get a function that looks like this. As it approaches 0, it goes down to negative infinity. That's the reflection of this part. And as it goes off to the right, well, it still approaches infinity, but very, very slowly, because this one approaches infinity very, very quickly. So these two are inverse functions. And let's go into our graphing calculator here and just kind of see where some of these points are. So here we have the point 2,4 on the exponential function 2 to the x. That's because 2 squared, or 2 to the 2 is 4. And on the right we have 4, 2, because log base 2 of 4 is 2. We'll talk a little bit in a minute about the actual definition of log. And I have the slider bar here. I'm going to change the base of the exponential function. Right now it's 2. I can make it go to the right to 3 to the x and to the left to like 1.5 to the x, or maybe 1/2 to the x. And we'll see how its inverse function changes as well. So we know that if I move this base to the right, the exponential function gets steeper and steeper. And so the point that you're seeing is still at x value of 2, but it's getting larger and larger. So here all the way up at 3, 3 to the 2 is 9. So that's why we have the point 2,9. But log base 3 of 9 is 2. That's why on the inverse function we have 9, 2. On the other hand, if I move it down, so as we get closer and closer to 1, they get shallower and shallower. They actually cross a little bit there. So even though it doesn't look like it, this green one is still the exponential. It still goes to infinity much faster than the red one. It's just that we have to zoom out a little bit to actually see where that behavior starts. If I go to the left of 1, then we remember that we don't have exponential growth, we have exponential decay. So exponential decay in the green. Now the red is still the inverse log, it just looks a little bit different. It gets flipped. Okay, so I just wanted to give you the basic idea of the shape. Now let me go back and we'll start talking about these things in a little bit more detail. The idea of being an inverse function is that log undoes exponentiation. That's always what an inverse function does. A function does one thing, its inverse function undoes that, it reverses it. So to give you an example that illustrates what I mean, let's try to solve the equation 5 equals 2 to the x. So it put in words, this says 2 to what power equals 5. Now we can think about this a little bit conceptually before we start doing the actual arithmetic to try to figure out roughly what do we expect. Well, we know 2 to the 1 is 2. We know 2 squared is 4. And we know 2 cubed that's 2 times 2 times 2, is 8. So if we think about it a little bit, what number squared, 2 to the what number gives us 5? Well, 2 to the 2 is too small. 2 to the 3 is too big. So that means that we expect our answer should be somewhere between 2 and 3. Just a nice little bit of a mental check before we go and do the arithmetic. And if you peek ahead, you see that we are going to get something between 2 and 3. But let's not jump ahead too much. The way that we're going to solve equations like this, well, the way that you always solve an equation is you want to get the variable by itself. You want x by itself on one side, and so you try to undo everything in the way of that. If you have an x plus 2, then you know that you subtract 2 from both sides, and that's because subtracting 2 is the inverse of adding 2. If you have something times 2, you know to divide. That's because that's the inverse. Same kind of thing here. We have 2 to the x, so we want to apply the inverse function to get rid of the 2. The inverse function of 2 to the x is log base 2 of x. So we take the log base 2 of both sides. Just like with any equation solving, we have to do the same thing to both sides to make sure they stay equal. So on the left, we have log base 2 of 5. That's some number, although we don't know how to calculate it yet. On the right-hand side, we have log base 2 of 2 to the x. And the whole point of log base 2 is that it undoes 2 to the x. So when you do log base 2 of 2 to the x, those cancel out, and you just get x. So what we get is that x is equal to log base 2 of 5. And at that point, we've kind of solved the equation. Now, we don't have a numerical value for it. And in fact, this isn't something that you can do by hand. But for right now, you can just trust me that log base 2 of 5 is about 2.32. And like we estimated, that's between 2 and 3. And in a couple of slides, we'll talk about how to actually figure out with a calculator what the numerical value for log base 2 of 5 is. For now, you should think about log base 2 of 5 as being this. It's the number, whatever number, such that if you do 2 to the power of that number, the 2 is because that's our base, you get 5. So this function is like, or this number is like asking a question. It says 2 to what power equals 5? And whatever the answer is, that's the numerical value that it's equal to. Okay, moving on. When the base of the log is 10, instead of like 2 in the last example or a in general, it's common for our textbook and for lots of math books to just write log instead of log base 10. Now, you're especially going to see that on most calculators. And we'll see it on our on-screen calculator in a minute. When it's base 10, you just write log instead of the 10. Now, you might remember from the section on exponential functions that we have the special number e. It's a mathematical number like pi, and it's about 2.71. Well, it seems like a weird thing to be the base of a log, but it turns out to be pretty useful in some ways that we'll see down the road. When e is the base, it's typical to write ln instead of log base e. The reason it's ln is because people call it the natural log, because e turns out to be a very natural thing to use as the base of a logarithm. And I think ln comes from natural log, possibly in another language where you would say the words in reverse. So ln just means log base e. Those are basically synonyms. Now on your calculator, you're probably only going to see 2 buttons, maybe even just one of them. You'll see a log button, that means log base 10, and you'll see a natural log button, that means log base e. But what if you want to calculate log with another base? Like on the last slide, we wanted log base 2 of 5. And you might say, well, my calculator doesn't have a log base 2 button. But there's a really interesting formula that lets you calculate log of any base using log of any other base. So for example, we can calculate log base 2 of something using log base 10 or log base e, or maybe you have a very weird calculator that only has log base 7. You could use that too. This is called the change of basis formula. It says that you can rewrite log base a of x, that's the thing you want to calculate, for example, log base 2 of 5, as log base c of x. Oh, I can tell I have a typo in my formula already, so let me fix this. Our change of basis formula says, there we go, if we want to calculate log base a of x, we can calculate instead log base c of x over log base c of a for any number c. It's the fact that it's for any number c that you get to pick that makes this convenient. So for example, that c should be whatever you have on your calculator. So we wanted log base 2 of 5 on the last slide. What our change of basis formula tells us is that we can make this log of 5 over log of 2. And I left a little gap here where I didn't write a base because we can put in any number we want there for the base as long as it's the same on the top and bottom. So it could be log base 10 in the top and bottom, and that's convenient because the calculator that we'll use on the screen in a minute has a log base 10. Or I could have made it a log base e, in which case it'd be a natural log of 5 over a natural log of 2. Or if you have that very strange calculator that only has a log base 7 button, it could be the log base 7 of 5 over the log base 7 of 2. So let's jump to our on-screen calculator here. And let's try to calculate this log base 2 of 5, which we showed on the last slide, or I told you on the last slide was about 2.32, I think. So the way that you do it on this calculator, your calculator might be a little bit different, but the way this one works is I need to open the parentheses, and then I say 5, and then the log of that. So that's the log base 10. We just use the log button, and when you don't see that, that means log base 10 of 5. So that means 10 to this number is 5. Now we divide, because our change of basis formula says that we need to divide by this log base 10 of 2. Then I'm going to open the parentheses again. We say 2, and then we say the log of that. Close the parentheses, and equal. And we get that 2.32. And we could have done the same thing with the natural log button, which we have here just to the left of the log button, instead of the log button. Okay. So we'll talk now about some properties of logarithmic functions. These are very much analogous to the properties of exponential functions that you might remember from pre-calculus. And these properties will simplify symbolic expressions and make a lot of our calculations easier down the road. So the first one says that if you have the log, this is for any base a, so you can kind of ignore the base. But if you have the log of x times y, so if you have a product of two things inside the logarithm, that turns into the sum of two things outside. So log base a of x times y equals log base a of x plus log base a of y. Multiplication inside turns into addition outside. Now, you might say, well, why is this true? That's kind of weird. Why does multiplication turn into addition? Well, if you think about some properties of exponentiation, if you think about, for example, 2 to the x plus y, one of the rules of exponentiation says this turns into 2 to the x times 2 to the y. So here, addition inside the power turns into multiplication outside. So with exponents, addition inside becomes multiplication outside, and log is the inverse function, so it kind of works in reverse. With logs, multiplication inside turns into addition outside. So just to justify this, let's take a to the power of the left and a to the power of the right and see what happens. So we'll do a to the power of log base a of x plus y equals a to the power of, and now we need big parentheses here for all of this to be together, log base a of x plus log base a of y. It would be incorrect to have just said a to the this plus a to that. You have to do a to the power of the whole side, and they don't split up like that because, just like we said, how do you split up a power where you have addition inside? Well, it becomes multiplication outside. So let's leave the left-hand side the same just for a moment. This becomes a to the log base a of x times a to the log base a of y. Oh, and you see I've already made a mistake because I wrote a plus here, and I meant a multiplication. So I just wrote that wrong. My apologies. That should be multiplication. Now, the whole point of log base a is that it's the inverse of a to the power of something. And that means, and we'll write this as one of our properties in a second, actually, that this a and this log a cancel. That leaves us x times y on the left. This here on the left, a and log a cancel. That just gives us x times, and then a and log a cancel, y. So we have x times y equals x times y. So one way to remember this, and I always forget if it's multiplication here and addition here or the reverse. So I always have to think, well, what's the rule for exponents? For some reason, that one sticks better in my head. That's plus inside the exponent turns into multiplication outside. And then I know that log is the reverse because they're inverse functions. And that's how I remember this. Okay, so that's property 1. Property 2, kind of the same idea, but instead of talking about multiplication inside, we're talking about division inside. So if we have a division inside, that turns into a subtraction outside. Now, why is this true? Well, once again, we can think about exponentiation. For example, if I did 2 to the x minus y, we have a rule of exponentiation that says if you have a minus sign inside, that's like 2 to the x over 2 to the y. A lot of times you actually learn this rule the other way, that if you see this, the way that you simplify it is that you bring the y upside, but as up top, but as a minus sign. We can justify this in the same way as before. So let's take a to the power of the left. I'll try not to make a typo this time. And a to the power of the right. So once again, we need parentheses to put this whole thing in the top. We'll use this rule of exponentiation that we just wrote to make this right-hand side, leaving the left alone for a minute, a to the log a of x over a to the log a of y. And then like before, all of the a to the log a's cancel. So on the left, we have x over y. On the right, this whole numerator becomes x, and this whole denominator becomes y. So we've justified the rule in basically the same way. Our next property is a little bit different, but it is still talking about how one operation inside becomes another operation outside, except instead of multiplication or division, the operation inside is exponentiation. So this is a rule that looks pretty weird, actually. It says if you have the log for any base of a power x to the y, then what you can do is you can take that y and you can move it out front as a constant multiplier. So log base a of x to the y becomes y times log base a of x. And again, this comes from our rule of exponents that says, a to the x times y is equal to a to the x to the y. It says that if you have repeated exponents, so this is an exponent and then another exponent, then you can multiply the exponents together. So let's justify this just like before. Let's take a to the power of the left and a to the power of the right, and see if we can find a way to simplify them both to get something where you have the left-hand side and the right-hand side are the same. Now, on the left, it's kind of clear what we want to do. We're just going to cancel the a and the log a, so let's do that right now. On the right-hand side, we want to cancel them, but we're not really in the right position because we have an a to the log a, but we also have this y in the way. So we're going to use this trick to try to group the a and the log a together, and the y is going to be left over. Well, what I'm going to do now is realize this is just multiplication. This is just y times another thing. And I can always reverse the order of multiplication. So let's write this as a to the log a of x times y. All I've done there is taken one thing times another and switched the order. But now it looks kind of like this, and so I can apply the rule where the x is kind of this whole thing, and that means I can group them together. So that's a to the log a of x all to the y. And this is what we wanted because the a and the log a cancel, and they give us x to the y, which is, of course, what we have on the left-hand side. So same kind of idea where we started with our two sides of our identity up here. We took a to the power of both sides, and we used the corresponding identity for exponential functions to derive a true statement for logarithmic functions. Okay, I think we have one more property here, really a pair of properties, and this is the one that we've secretly been using all along, so probably we could have written this as 1 or 2. This is just because log is the inverse of exponentiation. So this is the version we've been using all along, that if you have, this is the version. The second one is the version we've been using. A to a log a, they cancel out. You do exponentiation, then you reverse the process, and that means you're back where you started with, just at x. This is the same thing. If you start with x, or this is, you start with an exponentiation, and then you do a log, you're back where you started with. So I think I said that backwards. Let me try that again. So in this one, what do you do first? You do the log. So that's your function. You do the log, and then you reverse it by taking the exponent, and then you're back where you started with. This one here, you start with the exponentiation. We have to remember our order of operations. So you you take the exponent, then you reverse it with the log, and then you're back where you started with. So I think I've got a few examples queued up in a minute. We're going to look first at what the general shape of a logarithmic function is. We saw this on the first slide, but now that we know a little bit more about it, we can take a look. So this is the general shape of a log base a of x, when the base is greater than 1. Remember that when we're talking about exponentiation, we had two different versions. We had exponential growth when the base was greater than 1, and exponential decay when it was less than 1, between 0 and 1. And they had very different shapes. Exponential growth went up, exponential decay kind of went down closer and closer to 0. So it makes sense that the inverse function, the log, has very different shapes depending on a as well. So the exponential growth, we said, has its y-intercept at 0, 1, and then kind of looks like this to the right, and then approaches 0 to the left. So that means the log is going to have the reverse shape. The inverse is always the reflection across that line, y equals x. So it's always going to cross at an x-intercept of 1, 0. The reason is because a to the 0 is 1. That's a rule that we talked about. That means that log of 1 equals 0 because it has to reverse the process. Log of 1 is 0 for any base a. So it's going to cross 1, 0. To the right, it's going to increase slower and slower. It doesn't approach a certain number. It goes all the way up to infinity, but super, super slow. And to the left, it kind of shoots down to negative infinity as it goes to 0. For the other picture, if a is between 0 and 1, for example, log base 1/2 of x. Now, we're not going to see these too much. That's the opposite of our exponential decay. Our exponential decay went off to infinity on the left and then approached 0 on the right. So if you think about reflecting that over the line y equals x, you get our green line here. It still has our x-intercept at 1, 0, but now it approaches negative infinity on the right very slowly, and then shoots up to positive infinity as it goes to 0. So that's our general shape of a logarithmic function. Okay, here's what the example says, and this one's out of the book. Suppose that the population of Burkina Faso is estimated by the function p of t equals 14.235 times 1.029 to the t. Now this is an example that we did in section 1.2. I think there we were using the estimate 1.03, but here they're using 1.029, so it doesn't make too much of a difference. where t is the number of years after 2007, and p of t is in millions. So this is an exponential function that we looked at in 1.2, but now we are asking the reverse question. In that section, we said plug in a year, meaning plug in t, and see what the population is. But now we're asking the reverse. We're saying, in what year will the population reach 20 million? So if we want a population of 20 million, or 20 for p of t because it's in millions, what does t have to be to get that? This is exactly the job for an inverse function. Exponentiation takes you from the year to the population. Logarithms, its inverse takes you in reverse. It takes you from the population to the year. So that means we want to solve the equation 20 equals 14.235 times 1.029 to the t. Now, whenever you're solving an equation, your goal is always to isolate the variable that you want to solve for. So that means one by one, you want to move other things out of the way. Well, first, we've got this kind of this constant multiplier here. So we're going to divide it out to the other side. So 20 divided by 14.235 equals 1.029 to the t. By the way, if you look at this example in the book, I'm doing it a little bit differently, and I'm doing it in kind of an easier way than the book does. The book really only talks about two types of log base 10 and log base e, and doesn't think too much about other bases, but that makes these kinds of calculations more complicated. So for now, we're doing it an easier way. Okay, we're not done yet. We wanted to isolate t, but we know exactly how to do this now because we have an exponentiation, and we know that logarithms are the reverse. So to reverse 1.029 to the t, we want to take the log base 1.029 both sides. So log base 1.029 of the left-hand side equals log base 1.029, make sure we have some room here, of 1.029 to the t. Now the nice thing is that on the right-hand side, the log and the exponent cancel out and just give us t. And so what that tells us is that t equals this thing on the left. Now this is complicated, and we're going to need a calculator to figure it out, but the point is that this thing on the left here doesn't have any variables. It's just some number once we figure it out. And that's what t is. It's log base 1.029 of 20 over 14.235. Now, before we plug this into the calculator, let's just think for a minute about why this is the answer. You can kind of see, we did all the algebra kind of not thinking about the problem, but if you think about the problem, this should make some sense because we know that we're talking about exponential growth, so the population will grow by some multiple every year. We're starting in 2007 at about 14.235, and we want to end up at 20. So the first question is, when you divide 20 by 14.235, what multiple do you get? It's not double, that would be 28. It's something less than double. So this is some percentage of population growth. And this fraction tells you what percentage. We'll see what that is in the calculator in a second. But then what we're asking is, how many times do I have to raise 1.029, how many times do I have to multiply it by itself to get this growth? This will end up being something like, I don't know, I'm just going to guess, maybe 60% growth. This is 2.9% growth. So you're saying, how many times do I have to grow by 2.9% until I get 60%? The log does the opposite. It's going to tell us 1.029 to what power equals the growth that we're looking for. Okay, so let me bring up our calculator. Okay, we're going to start with 20 divided by 14.235. And we get 1.40. Okay, so my guess of 60% was off by a little bit. That means we're looking for 40% growth, 40.5%. And now we want the log base 1.029 of this number. But remember, this is the problem, is that I don't have a log base 1.029 button on my calculator. So we need to use the change of basis formula. That means we're going to calculate instead log base 10, because I have a log base 10 button, of the inside. So that's, well, I'll just write it as 20 over 14.235 divided by log base 10 of 1.029. So, or I could do that with log base 10, or I could do it with natural log because I have both of those buttons. Okay, so this is the numerator, and now we're going to take the log of it, and we get about 0.14. So that's the numerator. Now we divide by, I'm going to open parentheses just to make sure that this gets it right, 1.029, and the log of that. Close the parentheses, and now we get our answer of 11.894. But we don't stop there. We should go back and think about what the question actually asked. It said, in what year do we reach 20 million? Well, we found out that you get 20 when t is this. So just to make that really clear what I'm saying, what we just figured out here is that p of 11.894 equals 20. But what does this 11.894 actually mean? Well, this is the number of years after 2007. So we are about 12 years after 2007, between 11 and 12 years after. So that's about 2018 to 2019. And that's our final answer. Let's write it up here where we have some room. So if the question is, in what year does it actually hit 20 million? That to the left, the 2018, it gets close, but it's under. And then in 2019, it hits it and exceeds it. So if you're answering in what actual year does it happen, that's 2019, according to this estimation. Now, I want to point out a calculation that the book doesn't actually do, is instead of plugging in 20 and trying to find the t, let's just write the inverse function down. So for any function, you can find the inverse. And then if I plug 20 into that inverse, so if I did, we're going to find p inverse. And that means that if I plug in 20 and just do whatever calculation it says, I'm going to get whatever I had on the last slide, 11.894. So the way that we calculate an inverse is we try to isolate the independent variable. So I'm going to write p, and I'm not going to write p of t just for now because I don't want to confuse the of t in the parentheses for t actually being something that we're doing an arithmetic with. So here's our original function, p equals 14.235 times 1.029 to the t. And my goal is to isolate t. And you're not going to be surprised to see that we're going to do really the exact same steps as on the last slide. It's just we haven't plugged in 20 on the left. It stays as a p. So first thing we do is divide by the 14.235. And that's 1.029 to the t. And then we take the log base 1.029 of each side. It will cancel with the exponentiation here, just like on the last slide. And this is our inverse function. Now, I shouldn't really have written p inverse of t here because using t was a really bad choice of variable because you're not plugging in t anymore. You're plugging in the population. You're plugging in the population. You're doing the function, and what you get out is the year. Remember the original function, you take a year, you feed it through your function, and you get population. So the inverse, you put in population, feed it in reverse, and you get the year. So t is not really what you're plugging in. You're really plugging in capital P. So the notation here maybe was a little confusing, but the important part is that we have found our inverse function. And if you went and plugged in 20, you would see we have the exact same formula from the last slide, and we get in years 11.894. Okay, so that's everything I wanted to say in section 1.4. There were no parts that we didn't cover, but of course, as always, there are examples in the book that we didn't use because there are many of them. So you should please go and check on those and see if, if maybe the way I explained it was a little confusing, maybe you like the books way better, or maybe vice versa. But it's always a good idea to at least flip through the section in the book after you watch the video and kind of see any similarities or differences.